Hi, my name is Linda Ortiz, and this is Lab 4 on oscillations. The objective of Lab 4 is to examine the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. This is a two-part lab, where in the first part we will observe the motion of the spring mass system. Then we will use a model to predict the motion using Newton's second law. We will plot our observations and conduct a comparison with our model predictions. In the second part of our lab, we will introduce a second fundamental principle, the energy principle, that will compute the energy within our system. With observations and a model, we will determine if the spring mass system satisfies the energy principle. And as a main result at the end of our lab, we will determine that the spring mass system does indeed satisfy the energy principle. Here are the two fundamental principles within Lab 4, Newton's second law and the energy principle. The energy principle tells us that the total energy is conserved 0 if all the energy is summed up equals 0. And in this case, we will have the kinetic energy, potential energy of gravity, and potential energy of a spring. For observations, in Tracker, I've aligned the coordinate system so the positive y-axis is pointing upwards. The calibration stick will be 0.7 meters, which is given. There's a time step in between frames of 10.53 seconds. The mass within the video is 0.402 kilograms. The entire duration of the video is 9.3 seconds. As we are starting from rest, the initial velocity is 0, and here we have an observable unknown, which is the relaxed length of the spring. In order to find the relaxed length of the spring, we must first find the average swing period t. So here we have taken 3 different t's to find an average, add them all together, divide by 3, get 1.6 seconds. Then we use the average swing period to find the spring stiffness, which we find by 4 pi squared times mass divided by t squared. So here I found it to be 6.069 newtons per meter. And finally, I'll use the spring stiffness to find the relaxed length. From static equilibrium, we know that the force of gravity and force of spring can be equal to 0. Therefore, here we can set them equal to themselves. So I found the relaxed length to be 0.051 meters. Now onto the predictions that can be found within the code. I set up all my initial properties, where the ball's mass, position, velocity, time equals 0. This code will allow the model to extract data from Tracker earlier from what I observed. Here I have the gravitational force, spring constant, relaxed length of the spring, which I calculated earlier. Here I've included the 3 system energies that will be included in this lab, which are kinetic, the potential gravitation energy, and potential spring. Within our while loop, we define the initial energies, specify the net interactions, which are force of gravity, force of spring. F net here is the inclusion of force of spring plus force of gravity. The most important thing in this code here is that we constantly are updating things for the energy. So we're finding new directions and new lengths and new velocities that will update the kinetic energy. With new distances, we're updating the potential energies. So it's constant back and forth connection of updating, re-updating, in order to find and plot the different energies changes. Here I will show part of my animation for the model. And you see it successfully moves in the direction where Greco let go of the mass earlier. And this red here is the observed position that earlier in Tracker, and it seems kind of jumpy because it's only so much information, while the predicted goes really quickly. So model predictions. The blue arrow within the model was represented the spring force. The black arrow was gravitational force. Within the graph, the blue line was the delta K kinetic energy. The red is the potential spring energy, and the green is the gravitational energy. The yellow line down the middle, 0, is our total energy, and therefore concludes our observations earlier that all these energies will together add up to the energy total, which is 0. So here I've plotted observed versus predicted time. The blue line is the predicted motion from the model, and the red line is observed motion from tracker. Unfortunately, it started going away from each other. I believe this is from human error of not being on point, simply in real life because there's drag and because the predicted model is faster than the observed. So to answer, what does it mean? For your model system, is energy principle satisfied? Yes, it is satisfied. Delta energy here was 0 since we included everything in the system. Everything was 0 as proved by our graph with the yellow line. Using data you obtain in tracker, make two separate estimates of oscillation periods. First by estimating the period oscillation from the x position data, and second by estimating the period of oscillation from the y position data. Compare the two estimates and discuss. Well, I found the average time of one complete oscillation from the x and y plots tracker. X was 1.6, greater than the y oscillation of 1.52, and this is perfectly fine. Periods of oscillation for x and y are not the same and should not be, for different manners of calculating each exist and are not related. Masses on a spring sway left to right, similar to a pendulum in the x direction, while swinging up and down to y direction. It's perfectly fine that they're not the same. That concludes my Lab 4. Thanks for watching.